Hello and welcome to this session of ACS Science Talks, connecting the world through science. This is the virtual lecture series, scientific talks by specialists on specialized topics for a specialized audience. I'm Kunal Gupta and I'm pleased to be your host for today's broadcast of ACS Science Talks. I'm joined by my colleagues, Dr. Mihir Jha and Dr. Kaushik Natarajan, who will be moderating today's Q&A live. Now, with that, let me move to introducing our speaker for today, Professor Tajima. Professor Tajima received his Masters of Engineering and PhD from the Department of Chemistry and Biotechnology at the University of Tokyo. Following his PhD, Professor Tajima worked as a postdoctoral researcher at Northwestern University, USA, and before returning to University of Tokyo as a research associate in 2004, and later transitioning to the role of lecturer in 2009 and associate professor in 2011. Later in 2012, Professor Tajima moved to the RIKEN Center for Emergent Matter Science, where he currently leads the Emergent Functional Polymers Research Team in Supramolecular Chemistry Division. In addition to his appointments at University of Tokyo and RIKEN Center, Professor Tajima has worked on key projects with Japan Science and Technology Agency. Professor Tajima is also an associate editor with the ACS Applied Materials and Interfaces. His research endeavors and outcomes have led him to receive multiple awards, including the fifth Honda Fujishima Prize from the Electrochemical Society in Japan in 2009, the GCOE Lecturership Award from the University of Tokyo in 2009, Young Scientist Prize from the Minister of Education, Culture, Sports, Science and Technology Japan in 2013, and the SPSJ Hitachi Chemical Award 2018 from the Society of Polymer Science Japan. Thank you, Professor Tajima, for joining us. The stage is all yours.
Thank you. Thank you for your kind introduction. And I would like to thank the organizers in ACS for giving me this opportunity to talk about our research. I'm Keisuke Tajima, and RIKEN is a national institute in Japan, and I'm working on the organic electronics in general. And today I'm going to talk about the control of the molecular structure in the thin film toward the application of the organic electronics. The content of my talk today is divided into three topics. First one is the surface-induced molecular orientation in thin films, and also the surface-induced crystallization or structure control in thin film. And both are important for the organic electronics in general. I'm going to give you the brief introduction. And the third topic is a relatively recent work on the organic solar cell. And in this part, I'm going to show you the molecular design to control the molecular orientation in the thin films. All right. So why we care about the molecular orientation? Because in general, molecules are not ball shaped, right? It has a structural anisotropy in the shape. Good example for this anisotropy is the polymer, and particularly the semiconducting polymer in this case. And you take this PCHD, you can see that the polymer is long, right? And there's a high conjugation plane, so it's more like a ribbon-shaped molecules. So anisotropy is quite high. And how they align in the polymer film is really important. For example, if you imagine this, we call it the edge-on orientation, that the polymer chain is aligned to the substrate, parallel to the substrate, and the pipeline is perpendicular to the substrate. In this case, this seminal work, early work by Singhouse, show that the charge transport in the organic field effect transistor is really affected by this molecular orientation. This edge-on is better than this face-on, where the pipeline is parallel to the substrate. If you change the orientation situation like this, mobility in this direction is largely different. This one is much better than this face-on. So molecular orientation, edge-on is better for the organic phase effect transistor application. On the other hand, face-on is better for the organic photovoltaics or solar cells. And this one is demonstrated by several groups, but this particular example shows that the edge-on face-on difference gives you this difference in the performance of the organic solar cells. And another possible orientation of the polymer chain is end-on. I'm going to talk about it later, but this one is relatively rare compared to the other orientation. But anyway, each orientation have pros and cons. For example, edge-on and the face-on in terms of the light absorption. It's better than the end-on because you can imagine that the light is irradiated from this side. Transition dipole moment of the polymer is in this direction, so electric field is coupled better with these two orientations. So these are good for the light absorption or light emission, but the end-on is not good. In terms of the charge transfer, as I already talked about it, horizontal transport in offset is better with edge-on, and vertical is face-on is better. Of course, vertical orientation is better for the. It's probably the best for the vertical transport, and those are good for the each electronic devices. So orientation control in the thin film is very important for many optoelectric applications, I would say. So we want to control it, but how to control it is not trivial. So there is no general way to do it. And we've been working on this concept called surface segregated monolayer, SSM in short, for more than 10 years. And this is one of the earliest work from our group. So conceptually, this is kind of similar to the self-assembled monolayer, SAM. But this one formed on the surface of the film. What happened here is that this is PCBM, this is organic semiconductor. It's not polymer, but it's a small molecule. And we developed this kind of similar type of semiconductor with a fluoride chain attached. And this fluoride chain is known to have the low surface energy. Right? Surface energy is lower, much lower than the others. So it kind of surfactant in the organic solvent. So we mix two components together in the solution. And what happened here is that these surfactants cover the surface of the solution, right? And then when you spin coat this solution on top of the substrate, this surface segregated layer remain on the surface of the liquid film. And even after drying, this molecule have a monolayer formation on top of the solid film with this fluoride chain sticking out to the air part, because this is all about the minimization of the total energy. The surface energy is minimum with this fluoride chain pointing toward the air. So in this case, in this study, we show that this surface monolayer spontaneously formed on top of the PCBM film. This is the earliest work, and we can kind of generalize this concept to the many, not only for the organic electronics, but also for the many organic material. But we mainly focus on the application of this concept to the organic electronics. So so here's what typically happens when you do this spin coating from the mixture. So when you change the concentration of this surfactant fluoride fluorine in the solution, after the deposition of the film, if you measure the fluorine concentration by XPS, you can see that in the beginning, it's linearly increased and then saturated in this case. So saturation point is like 1 milligram per milliliter of this surfactant molecule. So what's happening here is first this surfactant absorbs to the surface, and then it covers the surface completely. At this point, this is saturation condition. Now above that saturation, this surfactant it's already occupied the surface, so it starts to remain in the bulk. And what happened here is that this is the contact angle of the surface, water contact angle of the surface, and you can see that this surface is getting hydrophobic. That is because of the fluoride chain exposed to the air, and then there is a saturation here as well. So it's kind of analogous to the Langmuir absorption isotherm here. So it behaves similar. Of course, fundamentally it's the same phenomenon. But the important point is that this monolayer remain on top of the solid film, and we can use it for the manipulating the property of the film. We extend this concept to the polymer, polyalkyl silicon in this case, and we design this molecule. This is also works as a surfactant, right? So alkyl side chain is partially fluoroalkylated, and the other did as a ordinary alkyl chain. And we mix these two polymers together. One is ordinary PCE DDT dodecile siphon, and the other is this surfactant. And what happened is similar to the previous case of the fluorine. The surface is covered with fluoride chain, and PCE DDT layer is on the bottom. This is monolayer. And yeah, the same surface segregated monolayer spontaneously form from the mixed polymer solution. And important point compared to the previous case, important point is the orientation of the polymer. So this PCDDT tend to have the edge-on orientation. So that's why actually we designed this molecule to have this matching of the structure to the bulk, and the fluoride chain could have a very high density at the surface of the film. So it behaved very well. And one thing I have to introduce is surface layer. It's a fluoride chain is hydrophobic, so it makes the surface hydrophobic. Other than that, this fluoride chain have a very strong molecular permanent dipole at the surface, and because this fluoride chain is aligning in the same direction, this dipole moment build up to form this surface dipole layer, and that actually affects the electronic property of the film. So this is the ultraviolet photoelectron spectroscopy of this film, and you can see that the shift of the ionization energy, that is the energy you need to take out one electron from film to the outside of film, right? So this usually, without this surface layer, it's 4.4, and then it gradually linearly increase with the concentration of this surface layer because of this dipole moment, dipole layer formed at the surface, and then it saturates. It's the same behavior as the fluoride concentration and the hydrophobicity. Important thing is that this ionization energy shift is really large, 1.8 eV. That is almost like changing the electron donor to the acceptor or something. So this fluoride chain, surface segregation of a fluoride chain could be very useful to change the electronic property of the organic semiconducting material. But I don't talk about it in detail in this talk about the electronic property. I'm mostly interested in the how to control the orientation of the polymers. So how to control it? As I said, PCDDFT case, this polymer tend to have a edge-on orientation. So like in this fish, the long fish, it's parallel to the surface. That is because the alkyl chain is have a relatively low surface energy compared to the pi conjugate system. How to control this orientation? Say this fish actually stand up and pointing, looking at the surface here. How to control this polyalkyl siphon into this direction in this orientation? And this is all about the molecular design. So we can use the same principle of the low surface energy fluoride chain, but we can change the design of the molecule. So we attach this fluoride chain at the end of the polymer chain. In this case, this fluoride chain tend to have the segregation on the surface, and because this packing, the main chain of the this surfactant tend to align vertically. You can imagine that, right? If you have enough concentration at the surface, and then if you mix these two together, this tend to crystallize inside the film, and this PCBT in the bulk also have the vertical orientation in the same film. That is what we found. So it's kind of orientation control from the surface, and it's kind of unique. You cannot find many examples of this end-on orientation in the polymer film, because usually, if you can imagine that the long chain tend to have the lining down orientation. So what's happened in this film is there is several things we can see the properties change. One thing is the optical property. So edge-on orientation give as I said, the light absorption better because transition dipole moment is aligned in parallel. So you can see that by using the spectroscopic electrometry, you can measure the absorption coefficient and the refractive index anisotropy in the film. So you can see that the parallel direction, you can have a large absorption compared to the vertical direction, similar to the refractive index here. But if you have an end-on orientation, it's completely opposite. So vertical direction, you have a larger absorption than the parallel direction, and the refractive index is the same tendency. So we can achieve the very unique, strong optical anisotropy with this one have also strong anisotropy, but its direction is different from the ordinary case. Another thing is, of course, the charge mobility. As I said in the introduction, we can expect the large mobility in the vertical direction. We measure this whole mobility by this space charge limited current measurement with a multiple thickness of the film. And what we found is that compared to these two situations, we got a much higher whole mobility in the vertical direction than this ordinary edge-on orientation. So large enhancement can be observed. And one thing is that silicon substrates tend to have the aligned tendency to have this polymer chain aligned on the edge-on, because it's kind of working as a low energy surface energy interface. But we can remove this edge-on oriented part on the bottom by modifying the substrate, and by doing that, we can get even higher whole mobility in the vertical direction, 10 to minus 2, which is actually quite high for the 3 active cycle. Okay, so as I said, this is conceptually achieved by the surface segregation and the molecular orientation control from the surface. What's next? So I talk about the 3 orientation. Last one is phase-on orientation. That is good for the OPV. So pi conjugate polymers as I said, tend to have the edge orientation. This planar pi conjugate plane is standing up. Like if you allow me to show my favorite fish analogy, the starfish have a vertically oriented. This plane is vertically standing up. Okay? What we want to do is we want to make this plane parallel to the substrate or surface, like this way. So how can we do it? So as I said, RP chain tend to have a lower surface energy, so it's natural to assume the edge on. How to do this orientation? So answer is what we come up with is that we have this branch RP chain, right? So what if we replace one of the branch RP chain with this floor RP chain? Then we can kind of expect that the floor RP chain tend to go to the surface, right? And then RP chain sticking downward. So this orientation allow, because this is directly attached to the pipeline, this pipeline could be face on. That is what we thought about how to control the face on orientation. And it kind of it's not perfect orientation, I would say, but it's worked. So let me show you the analysis. So XPS show that the fluorine accumulated on top of the surface. And it's similar to the previous examples. So firstly, there's no fluorine. Then if you start to add this in the solution, this fluoride chain accumulates on top of the film, and then it gets saturated around here. So its surface is fully covered with this fluoroalkylated NADI polymer. What about the molecular orientation? Well, it's really tough to analyze the molecular orientation on the surface. But one good way is NextApp. maybe you know that this X-ray absorption technique. This is collaboration work with Professor Yang in Taiwan synchrotron facility. And I don't talk about the detail of the measurement, but the important point is that we use this carbon 1s pi star transition of this X-ray absorption, and this transition dipole moment is known to have this direction, like a normal vertical to the pi plane. So if you know this path, by changing the incident angle of the X-ray, you can tell that this angle of the pi plane from the surface normal of the film. And you can see that the N2200, this is this NDI polymer here. This tend to have the kind of edge orientation after thermal annealing here. So that is, you can tell by this curve, angle dependence is the kind of positive dependence on the incident angle, right? So this is more like it's not perfectly edge on. It's close to the magic angle, but still it have a tendency like this. But if you have this fluorine alkylated NDI on the surface, you can see that the dependency is negative. So larger incident angle, you can get a smaller absorbance of the X-ray here, and the thermal annealing further enhance this anisotropy. You can use this equation to get this average tilt angle of this pi plane, and you can tell that this without anything on the surface, it's kind of edge on. It's not very vertical, but still angle is 57. With this Frankie chain, it's 40, 42. These are close to face on. So it means that this surface in the belly surface, this monolayer of the sclerotic version show the face on orientation. But does it affect the inside structure? After thermal annealing, we think we can affect the film structure. So here is the X-ray diffraction pattern. You can say you can actually estimate how much of the polymer is edge on and face on by analyzing this diffraction of the polymer film. And this here is the result. I'm going to go to this result in the table. So edge on rich in this ordinary polymer. But if you add the surface monolayer, after annealing, you can get the higher component of the face-on oriented polymer. And besides that, there's some diffraction here. You can see that it gets stronger, right? This is due to the pi-pi stacking. And this appears in the outer plane direction. That means that it's stacking like this way. So that means that it's even inside the film, it's getting the face-on rich component. All right. So yeah, here is the summary. So actually, face-on is the toughest challenge for us. But we believe that this concept also works for the to get this face-on orientation in the same film. And yeah, so for these 10 years, we've been working on trying to do this orientation control. And we believe that the edge-on, face-on, and end-on can be achieved in the polymer film. By, of course, we need to change the design in the molecules for each orientation. But if you do that, this surface segregated monolayer and induced orientation from the surface works very well for the to realize all the possible orientation. Okay, so the second part is related, but it's another challenge to control the crystal structure in the film from the surface. So you know that the molecule, when you crystallize, it's highly dependent on the shape of the molecule. But you know, of course, the surface when you crystallize the material in the film, the surface or substrate interface affect crystallization a lot, like epitaxial growth of the crystal. And you know, when you thermal anneal, it crystallizes, but these affect the structure and the crystallinity of the material. And we wonder if this surface segregated monolayer can affect this crystallization process in the film. And and we want to control it in our sorry, to get the preferable material property in thin film. So what we did is it's similar to the original molecular design. Is fluorine with the in this case oligosiloxane. This one oligosiloxane also have a low surface energy comparable to the fluoride chain, and it's a lot more flexible than fluoride chain. And we do this mixing and spin coating experiment for the fluorine derivative to get the molecular to get the thin film. And it works. I don't talk about the detail, but the silicon version also works as the surface segregate monolayer on top of the film. And what we want to do is that we want to control the crystallization process of the PCBM in the bulb. Actually, PCBM, lot of people think that it's amorphous, and it's true. As CAS film showed that many doesn't show any diffraction peak, just a ring shape, so it's amorphous. But if after annealing at the high temperature, say 150, it does crystallize. Like you can see these spots here, right? So it crystallizes, but it's multicrystalline, and the domain size is small, and also the orientation of the crystal is not aligned very well. So that's what typically happens for the PCBM film. But what we found here is that when you put this surface segregate monolayer on top of the film, first annealing temperature gets lower, 130 degrees it crystallizes. And at the same time, you can see that this multiple, lots of diffraction spots that is totally different from this pristine PCBM is appeared. So it's extremely high crystallinity, and you can tell just by this looking at this diffraction that there's a very good orientation of the crystal inside the film. And we analyze this pattern to get some idea of the crystal structure. But first, let me show you the AFM surface image. So this PCBM anneal film is crystallized, so you can kind of see the domain here, and you can even see the kind of hair-like crystal structure here, a microcrystal or nanocrystals. But if you put the surface segregated monolayer on top, after crystallization, you can see that the surface is much not more flat than this case. So it's apparently surface structure is very different, and the crystal domain is also different shape. Okay, so by using the X-ray diffraction pattern, we can get some idea about packing structure. We cannot solve it because information is too limited, but from the film X-ray diffraction, but we still get the optimum structure to reproduce this diffraction image. This is really kind of unique structure. It's got a very large lattice constant and 48 molecules in this lattice. And compared to the reported PCBM structure, there is several multiple crystal structure reported. But this is very different from the others. So that means that the surface monolayer not only promote the crystallization from the surface, but also crystallize this molecule into the different crystal structure. So it's induced a polymorph from the surface. And here is what we think that is happening. So this oligosiloxane version molecules have some certain orientation. So this fluorine is pointing down, and this molecule nucleate the crystallization here, and crystal growth propagate from the surface to the bottom. That is what we think. Another thing we notice by looking at this structure is that if you put the crystal structure, there is a kind of screw axis in this direction. This is top view, so it's kind of helical structure of the fluorine. So, and if this is induced from the surface, can we imagine that can we control the direction of this helix from the surface, because PCBM is not chiral, right? So it doesn't have a selectivity for the direction of the helix. But if you induce somehow from the surface, can we do this chiral formation of the helix? So we designed this similar module, but with this chiral point touch in the middle, and this S and our enantiomers are synthesized. And what we expect here is that this, for example, this S version induced a crystallization similar to the previous case, but this direction of the helix can be determined by this this molecule we choose for for the surface segregation. So this is what we expected. How to detect this? Yeah, of course, the circular dichroism of the film is important. So this is a little bit busy slide, but the first amorphous film before crystallization doesn't show any CD signal, and also this chiral material itself, film, doesn't show any CD signal. This silent. This is before annealing of the film. But after annealing, the crystallization happens similar to the previous case, and then you can see that this CD signal coming from this fluorine absorption, and it's a mirror image between this S and R enantiomers. So that means that it's probably happening. So in the bulk, this helix direction is determined by the enantiomer of the surface segment monolayer. So chiral SSM can induce a chiral crystallization. But is it really effect of the bulk? So to check this, we change the thickness of this base film. So you can actually, by changing the concentration, you can change the film thickness, and you can see that this CD signal increase linearly with the film thickness. That means that this signal, CD signal, is coming from the bulk of the film, not the surface. So it's proved that this chiral crystallization is happening in the same film. So here's the summary. So yeah, this is just the same thing. So chiral induction through the crystallization can be induced from the surface. We don't have the application for this phenomenon for now, but I think this is really open up the very interesting possibility to control the crystal structure in the film. So the generally surface monolayer can induce clarity or maybe priority. That we are still working on this possibility inside the film. So maybe application is the nonlinear optics or bulk spin filter effect in this chiral case, or this polarity can be, if there is a permanent polarity inside the film, it's gonna have a very good opportunity to use it in the also nonlinear optics and surface potential manipulation. But I won't talk about the application today because we don't know if it's really useful or not. But anyway, it's a kind of interesting phenomenon. Okay, so last part of my talk is the orientation control in the organic solar cell. We've been working on organic solar cell for years, and the important point is that even OPV, solar cell molecular orientation is very important. Just a general introduction of the solar cell is that maybe you all know that this type of solar cell have been developed and efficiency getting quite high, about 18–19% of the solar power homogeneity. And it got this advantage over the other inorganic solar cell. And this is one unique way to use it. This is our collaboration work with Sommer, Professor Sommer also in RIKEN. So they use this photovoltaics pasted on your skin and use it as a power source for driving this cardio potentiometer. Also consists of the organic semiconductors. But so yeah, because this one is very thin, you can use it as a very unique way. And general working mechanism of the organic solar cell is rely on this structure called mixed volatility junction. So typically we use this donor polymer and acceptor monomer molecules mixed together in the film, the thin film. And this kind of phase separated structure is the key for getting the high current in the organic solar cell. What happens is that incoming light is absorbed by the donor or acceptor, and then this interface between these two materials have some energy offset, and this is the driving force for charge separation between these two materials. So this is the general working mechanism. Important point is, of course, there is a lot of things you have to consider to get high efficiency in the organic solar cell. But the one thing is that, as I told you, these molecules have a largely anisotropic structure. So molecular orientation in thin film should be very important for the solar cell. And as I already told you, phase-on orientation of the polymer or small molecules probably good for the OPP. Okay, so how to control the modularization in thin film, especially in the mixed bulk junction film? So usually polymer is designed like extension of the pi conjugation to get a larger absorption or longer wavelengths of the absorption. So, but usually it's linearly extended like this. So this BT, this unit is very popular for designing polymers. When you extend the pi conjugation, you can imagine that the linear shape is probably the first thing you have to consider. But in our work, we extend this pi conjugation with this B-shaped monomer unit. We call it TPTZ. And what we expect here is that, okay, so this monomer unit, B-shaped unit is combined with linear shaped unit. This is just a coupling reaction to get a high molecular polymer. And this resulting polymer have a kind of zigzag copolymer, but we want to keep the planarity of the polymers because it's important for the charge transport or light absorption. But this, say, assuming that this zigzag-shaped copolymer can be obtained, it could change the orientation compared to this linear version, right? And we thought that this zigzag-shaped copolymer probably have a tendency to have the phase orientation in the film, and it's probably persist in the mixed bulk junction film. That's what we expected. So okay, let's see the orientation. So this is the zigzag-shaped polymer, and this is the acceptor, right? Unfortunately, this polymer is not that high, doesn't have a high crystallinity. It's almost amorphous, no peaks. And the Y6 have a strong tendency to have a phase orientation. That is good for the solar cell. And in mixed film, sure, we don't see any peak from the polymer. So it's actually not very useful to use the X-ray diffraction pattern for this kind of mostly amorphous film to know the molecular orientation in thin film. So what we rely on is that optical electrometry, like in the previous case. So this is good because you don't need to have the crystalline material. And average molecular orientation can be estimated by this optical anisotropy. So polymer film show this is the absorption coefficient in the in plane and the outer plane. This is the in plane, so parallel to the substrate. Outer plane is vertical. So outer plane is much smaller than in plane. That means that the transition dipole moment or say polymer chain align in plane in this polymer film. No, this cannot be obtained by the X-ray. The Y6 have a very strong optical anisotropy like this. So in plane is also very strong. And even in the mixed film, you can see that the bulk junction film have a large absorption in the in-plane direction. So it's a high plane of the molecules oriented parallel to the film plane. And we believe that this is helped by the shape of the molecule, especially for the polymer chain. So zigzag shape, you can imagine that this one is more stable with this orientation than the this way. Okay? So should works in favor for the exciton diffusion and charge transport if you have a phase orientation in the bulk junction. And yeah, we evaluate the solar cell performance. It's not very high compared to the state of the art system, but still, we got the decent performance with a relatively high fill factor. So even for this kind of amorphous film. Okay, so yeah, we still need to work on this similar concept on the state of the art system. Try to get this zigzag shape and make sure that this same concept works for the other system. Another thing we can do to control the molecular orientation is how to make the film. We can modify. So usually, bulk junction film is just a spin coating of a mixed two components, the polymer and the donor, acceptor molecules, spin coated on top of the substrate. This is the ordinary way. But another thing, recently it's getting popular to use this sequential deposition method. That is, the polymer is deposited first and dried, and then you spin coat this acceptor molecule on top of it. And then this Y6 acceptor molecules diffuse in polymer film very well. So resulting structure is close to this mixed bulk junction film. But the question is whether this process gives the same structure, or is there any difference, particularly in the molecular orientation in each domain? That is our question, and we tried this optical ellipsometry again. Here I show the graph with the order parameter in y-axis. That means that my negative 0.5 is mean that completely phase on or more like in-plane absorption, and 0 is a random. Right? So this polymer, this zigzag shaped polymer, have a very strong orientation in the in-plane direction. So that is good, and we was already observed. But when you compare the bulk junction film prepared by the mixed solution or sequential deposition, there is a large difference in the orientation degree. So sequential deposition give you the much higher order, in terms of the phase orientation, right? So this have a larger absorption in the in-plane compared to the mixed solution bulk junction film. So what we imagine is that by depositing polymer first, so polymer have a very high orientation, right? Then if you put this small molecule on top of it, this polymer orientation somehow preserved to some extent. It actually a little bit decreased, but it's preserved better than the ordinary mixed bulk junction because of this two component interaction. I can imagine that we can imagine that this orientation is not as good as the pristine film. So yeah, sequential deposition could affect the molecular orientation and lead to the higher orientation inside the film. And this actually reflected into the solar cell performance. Sequential deposition give you the much higher performance compared to the mixed solution. These are FM, but it's not important. It's almost the same structure, but if you look closely, orientation is different. So that's a combination of the molecular design and how to make the polymer film. Okay, so here's the summary of this part. So we think that the shape of the molecule is very important. Of course, that's we all know, but it's very powerful to control the molecular orientation in thin film. All right, I'm gonna close my talk by thanking our team member. This is the kind of old photo, but the work in my talk today is mainly done by Weichi Wang, Dr. Nakano, and Dr. Wang, and Dr. Chen, and Ms. Kaji. I really thank them for their hard work and also the funding. And thank you for your kind attention.